Alright, this is my second attempt at this video. I actually had it plugged in. Actually, I had to update the software that I use to capture my videos, and something made a change in the microphone or something. So I made the entire video once already, and it absolutely had no audio to it at all. So what I'm doing is I've actually had a request for a couple of problems to be done, or to go over some of the problems in the 2-1 section of work. So I wanted to do that, and I'm only going to hit the ones that were asked for. And if it doesn't cover something a question you've got, send me an email and we'll work on getting a video out for it. So we actually talked about the first two pretty much in the Google Meet the other day, and the question started about number 3 here, and like 3 through 12 are, well, I don't think 12, but a lot of these in this middle part are covered by just talking about this one. All you're doing is you're substituting in. So if the limit as x approaches c of k equals k, and the limit as x approaches c of x equals c, we're going to use those properties and the properties of limits to find the following limit. So what this part right here says is if you take the limit as x approaches anything of a constant, the limit's going to be the constant. And if you take the limit as x approaches c of x, then the limit is just going to be c, because you're just plugging in the c value here, because x is a polynomial. Polynomials are what are called well-behaved functions. That means, and you're going to learn more about these words later as you get through chapter 1, but it's continuous and differentiable. That's a well-behaved function. What it simply means is that we can take that c and just plug it in and find what the limit is. And that's exactly what we're going to do on this problem right here. So we want to find the limit as x approaches c of 5x to the 5th minus 7x to the 3rd plus x minus 2. All we're going to do is we're going to take c and we're going to plug it in. Now, the things that are actually going on in the background that you don't have to write down is you're doing this. You're taking the limit as x approaches c of 5x to the 5th, and then you're subtracting the limit as x approaches c of 7x to the 3rd, and then you're adding the limit as x approaches c of x, and then you're subtracting the limit as x approaches c of 2. You don't have to write all this out, but literally with a sum or difference, a product or a quotient, all 4 of those rules there now, a sum, difference, product, and quotient, you can break it up, take the limit of the individual parts, and then put them together. So I can take the limit of this one, and then take the limit of this one, and take the limit of this one, and take the limit of this one, and put them together with the pluses and minuses, and I've got the limit of the whole thing. So if you do this one, all you're doing is you're plugging it in. So you're going to get 5c to the 5th. And if you take the limit of this one, which we're subtracting, you're going to plug it in, and you're going to get 7c to the 3rd. And you're going to take the limit of this one, and you're going to add it in, and you're going to plug the c in, and you're going to get plus c. And then you're going to take the limit of this one and subtract it. And it doesn't matter what c is. Remember, the limit of any constant is just going to be that constant. So we have minus 2. So this is the answer for this problem right here. And that's all you're doing. Don't make it more complicated than it is. It's just showing you that you can plug in, and if it's a well-behaved function, and even some non-well-behaved functions you can treat this way, in certain parts of their domain, you can just plug it in and find out what the thing's going to limit, what the limit's going to be. And what this means is that if you've got this thing right here, that's a polynomial, it's the graph of a polynomial. It means that if you plug the value here, let's say that's c, it's going to be the same thing as what the value is approaching from both sides, because the function is well behaved. And as I said, you're going to find out later, it's also because it's continuous. But That's all you've got to do. Now, that one right there is going to cover number 4. You're going to do by substitution. You're just going to plug it in and find the thing. This one, you're just going to plug it in and find the thing. This one, you're going to plug it in and find the thing. Now, here's the thing, and we're going to talk about this in a problem in just a second. If this value right here had made the bottom 0, then we have to look at other possibilities. If it makes both the top and the bottom 0, it's called, well, we'll talk about it in just a second because I think one of the next problems has got that. But anyway, with this one, it's not causing a value of 0 on the bottom, so we're okay. So we're just going to go ahead and plug it in and find our limit. Same thing with this one, because negative 3 squared is going to give you 9. 9 minus 3 is going to give you 6, not a 0. This one, just plug it in, plug and chug. This one, same thing. This one, all we're going to do is we're going to actually put in values and find what these are. We're going to find 27 to the negative 0.1 minus 1 divided by negative 0.1. Put that value in here. And what you're going to see is, and you're rounding it 3 decimal places, but what you're going to see is this, as it gets smaller and smaller, notice we're getting smaller and smaller with the values we're plugging in, we're getting closer to 0. So we can see a pattern to these values and see that they should be approaching a certain value. All right, this one you're just going to have to plug it in and see, but then you're also going to talk about why you can't use substitution to determine the limit. And I'll give you a hint. It has to do with the fact that you can't take the square root of a negative number. Hint, hint, hint. All right, so this is the one that I was talking about earlier. If you plug in 10, you're going to take the limit as x approaches 10 of 2 times x minus 10 over x squared minus 100. And if you plug in 10 on top, you're going to get 10 minus 10, which is 0. 2 times 0 gives you 0. But more importantly, and guys, a 0 on top is not a problem. If we have any number down here, that means the limit's 0. If we have let me change that. If we have any number down here other than 0, we have a limit of 0. Here, though, when we plug that in, 10 squared is going to give us 100. 100 minus 100 gives us 0. This is called an indeterminate form. Now, for right now, what that means is try something else. In other words, it means to do something algebraically to this thing to see if you can alter it in some way. Now, if you're on top of your game here, you're going to see that this down here is a difference of squares, so you can factor it. It can be x minus 10 times x plus 10. Now, at that point, algebraically, we can cancel these two things out. So what we're left with now is the limit as x approaches 10 of 2 over x plus 10. Now, when we plug in 10 here, we're going to get 2 over 10 plus 10, which is 20, which gives me 1/10. Now, that is going to be our limit. Now, the question is, though, if you're going to have to think back on pre-cal just a little bit when we were talking about rational expressions. Remember, rational expressions are any expression that's expressed as a fraction. So this is a rational expression. Do you remember when we graph those, what happens at the place where we can cancel out? Well, if you remember, the 0 that happens where we cancel out, or the spot that the x value where it cancels out, that's going to be a hole. So at x minus 10, that's going to give us x equals 10. We have a hole in the graph, just an open hole. That's all it is. But here, x plus 10, remember if we solve that, we're going to get negative 10. When x equals negative 10, we have a vertical asymptote. So that's the difference in the two. The one that cancels out, that 0 is going to be, there's going to be a hole there. I keep saying 0, it's not actually a 0. It could be anywhere on the graph. But that factor is going to, that x value is going to give us a hole in the graph. And the one that doesn't cancel out is going to give us a vertical asymptote. All right, number 14. Okay, the INT of x, if you looked at the video for 2.1 part 2, that's where INT of x comes in. That's called the greatest integer function. And if you don't remember what it is, this is all that it is. It is the step function. So when we plug in x values, so if you plug in x equals 0 in the greatest integer function, we're going to be 0. What's going to happen is every value of x that we plug in up to, but not including 1, is going to round down and give us a value of 0 for the greatest integer. Now, as soon as that thing hits 1, it's going to jump up to a y value of 1, and the function's going to start kicking out 1 values from the point where x equals 1 all the way up to where x is equal to, is almost equal to 2. 1.9999 million nines. But as soon as that thing hits 2, it's going to jump up again. Now, notice my open dots and my closed dots. My open dots are on the integers. 0, 1, and 2. So essentially, the greatest integer function, what you're doing is you're just rounding down. So if we're approaching 5 from the left side, we're going to have values like 4.5, 4.75, 4.9, 4.999999999. But what's not going to happen? It's never actually going to get to 5. So when we take the greatest integer of a number that's almost 5, but it's not there yet, the greatest integer is going to round that thing down to a value of 4. So that's your answer right there. All right, now very similar to this is the absolute value graphs, or absolute value limits. When you're taking the limit, let me write this out here. We've got the limit as x approaches 9 from the right side of x minus 9 over the absolute value of x minus 9. Now, guys, when you're finding limits, think about what you're doing and just choose a value to plug in. What we're going to do is we're actually going to split this thing up. We're going to have the first part, we're going to talk about the sign that we're going to end up with, and the second part we're actually going to simplify algebraically. And I can't spell. Alge. Okay. So, the way we're going to do that is we're going to think about a number that's on the right side of 9. 9.1 is a good one. And that's what we're talking about when we're talking about this, finding out what the sign is. If we take 9.1 and we put it right here in the top, 9.1 minus 9 is going to give me a positive number. I don't want to know what the number is. I just want to know what the sign is. Now, if I plug the same thing in the bottom, 9.1 minus 9 is going to give me a positive 0.1. Then when I take the absolute value, it's still going to be positive. All right, so right now, I've done this part of my assignment for this. I found out that I've got positive over positive, which is going to give me an overall positive number for my answer. Now, I've taken care of the absolute value part when I had this plus right here. So now I've essentially got nothing more than x minus 9 over x minus 9, because I've taken care of the absolute value with analyzing the signs. And what is x minus 9 over x minus 9? It's just 1. So we have a positive 1 as our limit. Now, here's the issue. What happens if we go back, and I'm going to change colors here just so you can see where I make changes. What happens when we're approaching that from the left side? Well, if we're approaching this from the left side, we're thinking of a number like 8.9. So if we take 8.9 minus 9, we're going to get a negative number. So this is going to be negative. If we take 8.9 and put it in the bottom here, we're going to have 8.9 minus 9, which gives me a negative number in the absolute value, but when I take the absolute value, I'm still going to get this plus right here. So now I've got a negative divided by a positive, which is going to give me an overall negative value, and my x minus 9 over x minus 9 still gives me the 1. So that's the importance of doing your analyzing of the signs and plugging some number in just to see what the signs are going to do. All right, so this one we're using all of those properties that we talked about way back in the first part there, the sum, the difference, the product, and the quotient rules for limits. Remember, if we have the limit as x approaches a of f of x plus g of x, remember that we can just simply think about it. We don't have to rewrite it unless you just want to. Of f of x plus the limit as x approaches a of g of x. So we can take the limit of a sum and turn it into, break it up into parts, and make it the sum of two limits. We can do the same thing with subtraction. We can do the same thing with a product if we're multiplying. And we can even do the same thing with a quotient. And that's all you're doing right here. So for instance, the first one here, we've got the limit as x approaches 8 of g of x. And then I'm going to go ahead and split this thing up. Like I said, you don't have to write all this out, but this is the way you're thinking about it. And you're going to do plus the limit as x approaches 8 of 7. Now we already know right here the limit of a constant, regardless of what x is approaching, is going to be that constant. So we know that's going to be 7. And the limit as x approaches 8 of g of x, well, they told us it's negative 2. So then all we have to do is do that, and we're going to get 5. Now, same thing happens with b here, except it's a product. So in this case, we're going to split this product up, and we're going to find the limit as x approaches 8 of x, and we're going to multiply that times the limit as x approaches 8 of f of x. So now the limit as x approaches 8 of x is just going to be 8. And they told us the limit as x approaches 8 of f of x is 0. So we're going to get a 0 once we multiply those out. All right, the same thing is true with a power here. The limit as x approaches a of f of x squared can be thought of as the limit as x approaches a of f of x, and once you find that limit, then you can square it. Guys, you can pull everything outside of the limit that's a constant or a constant operation. You cannot pull functions out, you cannot pull x's out, or anything that's going to be varying. And then of course this one's going to be real easy. You're just going to have to write it or think about it like this. The limit as x approaches 8 of g of x, let me move that up. Limit as x approaches 8 of g of x divided by the limit as x approaches 8 of f of x minus the limit as x approaches 8 of 1. And once again, guys, you don't have to write all this out. This is just the way that you're starting to see them and start breaking them down. You're not taking the limit of this big whole thing, you're taking the limits of the individual parts and then putting those limits together at the end, or all in your head. All right, this one is fun. You need to know how to do a piecewise function. So we're going to draw the graph of f, and well, we're not even drawing it, we're just going to kind of go along here with this. But what you need to do is you need to make sure that you know what a piecewise function is. A piecewise function is simply a function that is defined in pieces. For instance, this part right here, the top, it is defined for all x values that are less than 5 to be this line right here, 4 minus x. Now think about 4 minus x. We can rewrite that and say negative x plus 4, and all that is that is a line that has a y-intercept of 4 and has a slope of negative 1. So we can, and that's for values that are less than 5. So we can automatically get rid of this option. We'll come back and look at that one. The y-intercept for this one is going to be way too high, so we can get rid of that one. And that has a positive slope, so we can get rid of that one. So right there, just looking at that first one, we're down to the point where this has got to be the graph. But let's go ahead and talk about it and look at it. So we do have a slope-intercept of 4. We do have a slope, or y-intercept of 4. And we have a slope of 1. We're going down 1 over 1, down 1 over 1, down 1 over 1. So that part right there is verified. Cha-ching. Now this other one here, for some reason, students always get tripped up when they see an equation like this. Guys, this is still a line. Now this line is defined for x values greater than 5 to be x over 5 plus 1. So x over 5 plus 1. Well, all you're going to do is you're going to think about this as 1/5 times x plus 1. You're just going to separate that x over 5 into 1/5 times x. And if you're having trouble seeing that, remember x is just x over 1, so now when we multiply this fraction, we still get the same thing. But I want you to start making sure that you can break those things down and see what they actually are. So now we have a slope of 1/5, that's a positive slope, and we have a y-intercept of 1. Now, the thing is, our graph is starting over here at 5. So we're going to have to kind of track it back and make sure that we're going back, and that looks like it's going to work out. It's not going to be an exact science, especially with one of these. If you're actually graphing it itself, you could actually count it. 1/5 is going to go down 1 and back 5. Down 1, 1, 2, 3, 4, 5, boom, right there is my next point. So that one does work out. So now we know this is the graph, and we want to determine the limit of this function as x approaches c from the left, and the limit as x approaches c from the right. So what we're going to do is we're going to zoom in on this video a little bit, or zoom on this graph a little bit. And as we're coming in to 5, because it tells us that c is 5, but we're approaching it from the left, that limit is going to be negative 1. So this first limit right here, the limit as x approaches 5 from the left for f of x equals negative 1, because we're approaching the value of negative 1. Remember, the value that we're approaching, the limit, is the y value. What y value are we approaching? We're approaching negative 1 as x gets closer and closer to 5. And then the limit from the right of f of x, we're following in, coming in, coming in, coming in, getting closer and closer to 5 from the right side, and we're approaching a value of 2. So the left side limit as we get closer to 5 is negative 1, the right side limit is 2, and part C, does the limit as x approaches c exist? Well, right there, because we're approaching 2 different values, we know no, the limit does not exist. So the answer for that one would be no. If so, what is it? Well, it's not. It doesn't. If not, explain. Well, it approaches 2 different values from the different side of 5. From the left and the right, left and right limits approaching 5 are not the same number, therefore the limit doesn't exist. Remember, that's one of the reasons why a limit doesn't exist. We're approaching two different values from the two different sides. All right, so that is all the questions that were asked for this. If you're having trouble with any of the other problems on this, guys, send me an email, let me know. I'll put together a video. Hopefully I've got it fixed now where I won't have to make 2 videos to be able to send one out. But I hope that helped, and let me know if you run into any problems.